So we're skipping to 2.8. It's about subspaces. So we just made up a new word. So we're going to define a subspace as a set of vectors that have a certain property. So we'll say a set H in Rn, so it's Rn, a set that contains Rn vectors. We'll say it's a subspace of Rn if it meets the following three criteria. So the first one is H has to contain the zero vector. So the zero vector has to be in there. H is closed under addition. So what that means is if you add any two vectors in H, the resulting vector that you get has to still be in H. Okay, so it has to, we call that closure. So the operation doesn't send a vector outside of the space that you're already in. Okay. And H is closed under scalar multiplication. So if you scale a vector in H, then the scaled vector has to still be in H. Yes? It's closed under addition. And 3 is closed under scalar multiplication. So both of those are called closure. Closure, right? Closure under addition and closure under scalar multiplication. So since every subspace contains a zero vector, then every subspace must include the origin. So these are R2 spaces. So we want to know, are these subspaces? So if I look at both of these, the zero vectors in both, right? So that's in both of those. If let's say I take a vector in this H and another vector in this H, if I add them together, is it still going to be an H? We're going to assume that these go out forever. Okay, this is the whole second quadrant. Okay, the entire second quadrant. So if I add these two, right, that's still going to be in H, right? If I take this vector and add this vector, right, the result will still be on that line. So the problem happens when we do the scalar multiplication. So on this one, if I take any vector in H and I scale it, I could scale it, say, by 2. I could scale it by -1 or whatever. It's still going to be on that line. So that's a subspace. So this one is a subspace. But here, let's say if I take that vector in H and I scale it by -1, it's going to be right there, which is not in H. So this one fails closure for scalar multiplication. If I multiply it by negative, it's not going to be in the second quadrant anymore. Right. So this is not a subspace. Everybody get the attendance? Okay. So for any set of vectors in Rn, if they're all the same size, then the span of those vectors is always a subspace. So the span of any set of vectors automatically is a subspace. So let's see if we can prove it. So we need to show first is the zero vector in, we'll call it H, the span, I almost wrote spam, the span of these vectors. So is the zero vector in there? You tell me. What does the span of those vectors mean? What does that mean? Sorry? It's all the linear combinations, right? The span of the vectors is a set that contains all the linear combinations of those vectors. So here's one linear combination. Right? And that would be the zero vector. Do we agree? So that one checks. Zero vector is in H. Our H, what we're going to call the span of V1 to Vp. So the answer is yes for that question. The second thing we check is closure under addition. So H1 plus H2, we'll say is this in H. If H1 and H2 are in H. So if I take two vectors in H, and I add them together, is it also going to be in H? So these are vectors, okay? Vectors in H. Well, if they're in H, that means they're in the span of the vectors V1 to V sub P. So that means these are linear combinations of vectors of P, both of them. So we'll say H1 plus H2 is what? So H1 is a linear combination of the vectors V1 to V sub P. So I'll just say it's like A1 V1 plus A2 V2 A sub P V sub P, right? Plus H is also a linear combination. It could be a different one. We'll call it V1 V2 V sub P V sub P. Right? All those V's are vectors. So this is H1. This is H2, right? Because they're both in H, that means they have to be linear combinations of the vectors V1 to Vp. Do we agree with that? So let's combine the V1s. So this would be A1 plus B1, V1. Right? And combine the V2s. And you could do that with all of them. Whoops. And what is that? That's a linear combination of the vectors v1 to vp. So h1 plus h2 is also a linear combination. So that means h1 plus h2 is in, this has to be in h. Then we got one more thing to check. We need to know if a scalar multiple of any vector in H is still in H. So the question is say C times H in H if H is in H. So big H is the span of V1 to Vp. Little h is one of those vectors. And we want to know is if we scale a vector H, is it in H? So C times H is C times, and I'm going to write H as a linear combination of the vectors V1 to Vp. So I'll call it A1, V1, A2, V2, all the way to the end. Right. Yeah. Big H is the span of the vectors V1, V2, all the way up to V sub P. So that means the span is all the linear combination of those. So if I say that a vector is in the span of those vectors, that means I could write it as a linear combination of those vectors. Okay. Right. So if I say H is in, little h is in big H, this is a vector in what we're calling the subspace, right? If it is a subspace, that's what we're trying to figure out. If little h is in H, then that means little h is a linear combination of those vectors V1 to V sub P, because big H is the span of those vectors. It represents all the linear combinations possible. So H is one of those, little h. Little h is one of those vectors, right? So I just rewrote H as a linear combination, and then I can distribute the C, right? And that is not the same linear combination, but it's still a linear combination, right? I've got scalars times each vector, and they're all added together. So that is still in H. So CH is in big H. Those are the coefficients of the vectors, right? It's a linear combination, right? Linear combination, those are the scalars that we're multiplying by each vector. So all three were satisfied. So H is a subspace. And when you finish your proof, a lot of times you just draw a box at the end. Some people draw a box and write QED in it. QED is it's the first letters of a Latin phrase that means this is proven, basically, or something like that. So we are going to do this for other examples. Okay? So we are going to do proofs. These are, some of the simpler proofs. And I'm going to do some examples. So let's do this example. There's more. We'll do several. So it says, which of the following are subspaces of R3? So here's one example. So this is H is, and this notation is set bracket notation. So this tells you, the first part, the X, Y, Z, that tells you what kind of vectors are in the set. So these are R3 vectors. And this tells you the property that they have to adhere to be in the set. So this is the condition that must be met. So these are all XYZ vectors such that, that's what this line means, this vertical line. You say such that. So all these such that this is true, right? This property holds, okay? So H is all the R3 vectors such that 2x minus y plus 3z is equal to 4. So any vector where that holds is going to be an H. And we want to know, is this a subspace? So we're going to check the three properties. So number one, what's the first one? Zero vector. So is is 0, 0, 0 in H? So somebody says no. What do you guys say? Well, 2 times 0 minus 0 plus 3 times 0 is not equal to 4. Right? So it's not in there. So the answer is no. If one of these fail, it's not a subspace. All three have to hold in order for it to be a subspace. Okay? So once you find one that fails, then you can stop. You don't have to keep going. And the zero vector is an easy one to check. Okay, you just check to see if you have the zero vector in there. Everybody okay with that? If that was equal 0, different story, right? We'd have to keep going. But because we have the 4 on the end, we can't say it's a subspace. That was an easy one. All right, this one has 0. 0 on the end. So is 0 in H? We're going to say yes, right? So we plug in 0, 0, 0, we get 0. So the zero vector is a solution to that equation, right? So we're good. So number two, we're going to see if we pick any two vectors in H, is the resulting vector, is it also in H? So the property is that the components of the vector have to solve this equation, right? So we have to pick two vectors that are solutions, and then we add them together and see if the result is also a solution. And if it is, then we have closure with addition. Okay. So I'm going to pick.
So any of them work, doesn't matter. Like, one, two, linear combination of that here.
We don't have to do linear combination, just two vectors. So linear combination of 1 and 1 times the vectors. You just add the two vectors. That's all you need. So we're going to pick two vectors in H. They have to be arbitrary. They have to be general vectors. You can't pick one example of, you can't pick two examples. You have to pick any two vectors that are solutions. So we're just going to give them names. Let's call them U and V. Okay. So we're going to pick any two solutions to this. This equation has infinitely many solutions, right? You've got one equation and three variables. There's infinitely many. It's actually I think it's a plane. It's a plane R3, right? So there's infinitely many solutions. We're going to just pick two vectors, and they can be any. All we know is that they're solutions. Okay. So so we'll say U is, let's call U U1, U2, U3. Is that good? And V will be V1, V2, V3. So these are vectors, and these are the components of the vector. Okay. And I'm going to add the two. So what would be U plus V? Yeah. Just add the components like this. So what I need to show is that these, if I plug these in, it's a solution also, knowing the fact that U and V are solutions in themselves. Okay? So what I'm going to do is plug that in to my equation, see what happens. So 2 times U1, right? I'm looking at first component here. They call it X. Our first component is U1 plus V1. I'm going to plug it in for that X. Okay? So 2 times U1 plus V1 minus Y. My Y component is the second component, right? U2 plus V2. And what's the last one? Plus 3Z. Z is the third component. So I've plugged that in. This is X, Y, and Z, okay? Well, we got to show it equals 0. And we can. So let's get rid of the parentheses. 2U1, 2V1, minus U2 minus V2, plus 3U3 plus 3V3. Let's get rid of the parentheses. So next, I'm going to group all of my U's together And I'm going to group all the v's together. I just rearranged it. So I've done the hard part. That was the hard part. So what is that? Huh? So this is vector u, and that's first, second, third component of u, right? And it's u plugged into this equation. Do we agree with that? So it's 2u1 minus u2 plus 3u3. So what does that equal? It equals 0. How do I know that? Because I chose u to be a solution to that equation because I said u had to be an h, right? So I said let u and v be any two vectors that are in h already. So they're already solutions to that equation, right? The components are. Does that make sense? So there are solutions. I know they're solutions. And that is vector u plugged into that equation. So that is 0. What about this one? That's the same thing because v is a solution. So that's 0. So this is all equal to 0. That means that u plus v is in h. So we've proven the second condition, the second criteria. Everybody okay with that? Any questions? We just jumped into some heavy duty stuff. You guys got real serious all of a sudden. Paying attention, I like it. All right, third one, we have to show that it's closed with scalar multiplication. So I want to know is, we'll say C times U in H if C is any real number, it's a scalar, and U is already in H. So I'm going to pick a vector in H. So that means the components are the solution, or is a solution to that equation. And I want to know, is a scalar multiple of that also a solution? So C times U is this, right? So the way I'm going to check to see if C times U is in H is I'm going to plug C times U into the equation. And I'm going to show that it's equal to 0. If it's not equal to 0, then it's not. If it is equal to 0, then it is. It satisfies the equation. Right? So 2 times the first component minus the second component plus 3 times the third component. Whoops, forgot the C. So if this satisfies that equation, then I'm good, right? So I need to show that's equal to 0. So can I do that? Tell me how. What do I do first? Factor out the scalar, good. So there's a scalar factor in every term, so I factor it out. Okay. And what is this guy right here? 0, because u is in h. It's a solution to that equation, right? So that has to be 0. And c times 0 is 0. So we did it. All right. So, sorry. So c u is in h. So that satisfies the third one. It satisfied all 3. So H is a subspace. These are not good questions in MyLabs Plus. Right? Does that make sense? The work is the answer. Okay? We all, the answer could be, is it a subspace or not? Yes or no. I don't care necessarily which one it is. I just care that you knew how to go through and you check the 3 things and you do that correctly. That's what I'm going to be checking. So this is definitely show work material. Okay. So I can't grade that on your homework, but you can always bring it to me and I'll look at it, or you can when you take your quiz, I'll grade that work. So I'm definitely going to have to grade these pretty closely, right, to see if you're doing the right thing. I think there's another one. So here H is defined by a vector where it's 5 times x, 3 times x, negative 1 times x, where x can be basically any real number. It says an arbitrary number. That just means any real number. It could just be any number. Okay, so x can be any number. Okay, so we want to know, is this a subspace? So is the 0 vector in H? Yeah, because we can plug in 0 for x, right? X can be any number, right? So let x be 0, then 5 times 0, 3 times 0, negative 1 times 0 is the 0 vector. So yeah, the 0 vector is in H. Okay, we're going to add 2 vectors, u plus v. And I'll do them by columns instead of these. I hate these row vectors. Let's do columns. All right, so u is, let's say, 5 times x1, 3 times x2, and negative x, sorry, I need to pick the same one every time. So that's my vector u. And then v looks very similar, except x is some different number. We'll call it x2. So we're going to call that v. Right? So those two are in H. That's obvious, right? x1 and x2 are just any numbers that we, whatever. I don't know what they are. They could be anything. So I'm going to add them together. So let's factor out the constants. Do you agree with that? So this is 5 times a number. This is 3 times that same number. This is the negative of that same number. So that is in H. Right? That's the definition of what H is, right? It's a vector like that. So H is all the vectors that look like this. Right? And that's one of those. So U, I picked an x1 and multiplied by 5, 3, negative 1. And for V, I picked an x2, right? Well, x1 plus x2 is another one of those numbers that you could multiply by 5, 3, negative 1 and make a new vector, right? So that's also an H. Okay.
The only way to fail this if one of the terms doesn't have a variable in it? I don't understand how this ever fails.
It can't fail because it is a subspace.
That's what I'm saying. If it's not a subspace, it'll always fail. But how do you tell like what fails about it?
Well, we did the first example. It didn't have the zero vector, I'll show you. If we had gone further, then those others would have failed too. They don't all have to fail, but others would have failed. This one that's equal to 4, right? When you do the addition here, these would both equal 4. So when you add them, you get 8. Right? It wouldn't be equal to 4. So the sum wouldn't be a solution, right? So that's what you would find stuff like that. Okay. Yep. But we just stopped on that one because we just we knew the first one was done. So sorry. Yeah, it has to be a number. But it could be any number. Right, that wouldn't. Well, right. It would fail to 0, yeah. Yeah. They don't have to be, but they could be. X1, X2 could be different, so I'll give them different indexes, yeah. Because, they could be the same, or they could be totally different. If I'm letting U and V be 2 different vectors, then the X1, X2 would have to be different. So I'm just letting them be different. So these are just any two vectors in H. So I have to label them differently because they could be different. And then just show that the sum is also one of those vectors in H. Has the same property. That vector has the same property that H says you have to be at H. Right? So that's what we're talking about. All right, so let's do C times U, a scalar times vector U. Well, let's say that's C times 5 times X, 3 times X, negative X. Right. I don't have to use X1 here because and then I multiply the scalar inside. C times 5 times X, C times 3 times X, negative CX. So this is 5 times C times X. Right? X is any number and C is any scalar, which basically mean they're the same, kind of the same thing, right? They're both arbitrary numbers. So C times X is an arbitrary number. So it's one of those, it's the same type of vector. And so this one is a subspace. That is one of those vectors in H. Because the components are 5 times some number, 3 times the same number, and the negative of that same number. It's the third component. So that's one of those vectors in H. So it's closed with. It's still a vector in H. So U is in H, so that's why I wrote it like this. And C is any constant scalar. And then I can show that that vector is still a vector in H, right? Yeah, they're different. Yeah. I'm going to show you an alternate way to do this one. Yeah.
So is it only if you have a situation passes the first one, it's true vector, and fail the other two? So far it's passed the first one, it's passed the other two.
Yes, you can pass the first one and fail the other two. Maybe. Let me see. I can make up one if you'd like. Maybe.
Like it doesn't scale, but it'll add zero vector.
I'll try to make up one. See if I can come up with one. But yeah. So this vector is the same as this, right? Okay, well, this is, if X is any number, any real number, then this is the span of this one vector, right? So we're done, right? Because the first thing we proved was that the span of any set of vectors is a subspace automatically. And we already did all the work to show that. Right. So this is a span of 5, 3, negative 1. That's this H is equal to the span of this vector. Whoops. That means those solutions that you got where it was the span of a vector just by itself or the span of two vectors, all those systems have solutions like that. Those solution sets are subspaces. That's why we're studying subspaces. Now the ones where it adds this other vector to it, then that may be different. Okay. All right. Let me trying to think of an example to show you, but let me see if I can find one out of the book that fails. Yeah.
He says it's H equals the span of 5, 3, negative 1. And 5, 3, negative 1 is the point in R3.
It's a vector in R3. It's a vector in R3, and the span of that vector is it's a line, right, in R3. Yep. So let's say H is all vectors, say x, y, such that x times y is less than 1. So the 0 vector is that in H. Well, 0 times 0 is less than 1, so that one checks. Let's skip to the third one. And I'm going to choose a vector in H as a counterexample. So to prove that it's not a subspace, all you have to do is come up with an example where it fails. Okay, you just need one where it fails. So that vector's in H. Do we agree? So if I multiply -1/2 and -1/2, I get +1/4, and that's less than 1, right? So that didn't work. Hold on. Oh yeah, that's in H. Yeah. So let's scale it.
That's two right on.
Let's multiply by 8. So this vector is in H. So let's multiply it by 8. So we get -4, -4. And when you multiply it, you get 16. So that's bigger than 1. So that one fails. So this is not a subspace. It's a good question. I should have talked about what do you do if you think it fails one of these and you just need to come up with an example where it fails. You could do all the work and you could show through the proof you can show that it doesn't work, but or you could show that it's not clear or whatever. But to show, all you have to do to show that it fails is to find a counterexample. Does that help? So you need to check all three independently, But if you have a suspicion that one of them fails, and start with that one. Do that one first, and as soon as you show that one fails, you don't have to do the other two. Okay? Start with the one you think fails, and then you can move on. Okay. So the next one's called basis of a subspace. So a basis for a subspace H of Rn is any linearly independent set in H that spans H. So you've got a subspace H. If you have a linearly independent set of vectors that span H, then those set of vectors is called a basis. So this can be thought of as the minimum set of vectors that spans a subspace. You can span the subspace with a lot of vectors, but to make sure that they're all linearly independent, that whittles it down to the minimum amount that you would need. Okay. So we already talked about this a little bit. We said that the columns of the identity matrix E1, E2 through E sub n, we called those the standard basis vectors of Ren. So we did this a lot when we were doing transformations, right? In R2, right? E1 was 1, 0, and E2 was 0, 1. They are linearly independent. Right? If you put those in a matrix, they're already row reduced, right? To the identity, right? So they're linearly independent. And I have two of them. And in R2, you just need two vectors to span R2. So this is, if I put E1 and E2 in a set, it's called a basis for R2. And this is actually the standard basis. Okay. It's the standard basis of R2. So any vector B in Rn can be written as a linear combination of those basis vectors. So that's what makes them a basis, is that they span the set. So you can write any vector as a linear combination of those vectors. But the basis is unique in the fact that it's the minimum amount of vectors that you need to span. But you can have different basis vectors for the same space or subspace. So the standard basis is not the only basis for R2. You can come up with others. Okay. Any two vectors that you can row reduce to the identity is a basis for R2. Okay. So any two vectors that aren't multiples of each other is a basis for R2 if they're R2 vectors. Any two R2 vectors that aren't multiples are a basis. Right, this is just reminding you about stuff we've talked about, right? So the columns of a matrix A are linearly independent if the system AX equals 0 has only the trivial solution. The columns of an m by n matrix A span Rm if and only if A has a pivot in every row. So that's spans Rm because the vector sizes are Rm vectors, right? If the columns of the matrix. Okay, so we want to know, do the following vectors form a basis for R3? And why or why not? So what I want to know is, I've got three vectors in R3. They have to row reduce to the identity matrix. If they're linearly independent and I have three of them, and there are three vectors, then three linearly independent R3 vectors span R3. That makes them a basis. So do these row reduce to the identity? Yeah. So if I put these in a matrix, it's triangular. This is called upper triangular. Then it will reduce to the identity. Yes. What about this one? I don't have to reduce it. Will it reduce the identity? Why not? I can switch rows. I agree with you that it will not reduce to the identity, but not for the reason you said, right? So this one is not a basis for R3. See if you can tell why. Why? Can you tell by looking at it? All right. Well, we'll say this is vector 1, this is vector 2, this is vector 3. So vector 3 is vector 1 plus vector 2, right? Yeah. So vector 3 is a linear combination of the other two, right? So they're dependent, right? So these are dependent. So this is no. They're dependent vectors. So this is one of those where if this is a test question, this should take you 5 seconds, okay? But you could take a lot longer and still get the same answer, but you know, this would save you time if you just look at it for a minute before you throw it in the calculator, you know. You don't have to throw it in the calculator first thing. Take your time, sweet talk a little bit. Okay? Just jump in. Sweet talk the matrix a little bit. All right, so find a basis for the subspace R3 spanned by the following vectors. So I've got too many vectors, right? These are dependent vectors the way they are. I want to see which of these vectors can I choose to make a basis. So I need 3 of the 4 vectors. I need to know which 3. I'm sorry? So the first 2 are multiples? Okay, well, are any of the others multiples of each other? So I am going to put this in the calculator. Please, please, please do not draw the line here. The system is not this equals that, okay? These are just the 4 vectors. If you're going to augment, you need to augment with 0. Because you're going to see if AX equals 0 has the trivial solution or others, right? But all I really want to know is which ones are independent from each other. Okay? So I'm going to throw this in the calculator. We already know they're dependent, and we can see, yeah, you're right, the first 2 are multiples. I don't know about the others. You know, is there a way to combine the others to get, you know, it may turn out that we don't have enough linearly independent vectors. Okay, so if that happened, then we couldn't get a basis for R3. So we'll see. Sorry? We may not, you know, we have 4 vectors here. We may not have 3 independent vectors. We may only have 2. So, you know, I'm going to check and see which ones I can call independent. So here's a way to check. It's not the only way, okay? So I'm going to row reduce it. All right. So the columns that have pivots correspond to the columns that are independent. So the first and third vectors are independent from each other. So, you know, if I just eliminated these 2 and I just row reduced this, right? What would be the only solution? The trivial solution, right? So that means those 2 are the ones that are independent. So we cannot span R3, but, you know, it's actually asking, find a basis for the subspace spanned by these vectors. So if you span these vectors, you get a subspace. What would be a basis for the subspace? All I need are the first and third vectors, and I can come up with the rest. Okay, so the basis is, we like to give it a name I like to use beta for basis. It's a Greek letter beta. And it is a set that has the vectors inside of it, okay? So it's not enough, I'm sorry, it's not enough just to write the two vectors. And you can't write the two vectors in a matrix. That's a no-no. They are vectors separate, and you need both vectors, okay? So I'm going to write the vectors in here, separated by a comma. So that's the basis for the subspace that you get when you if you span any set of vectors, you get a subspace. If I span these, it's all linear combinations of those four. I could actually simplify that and say it's really all linear combinations of just these two, and I don't even need those other two vectors. So I had four. I actually only need two to span that subspace. The span of these is equal to the span of those. They're the same. You get the exact same vectors. Because I can write these two as a linear combination of these two. So yeah, because they're dependent, right? So I don't need those other two. I can just use the first and third, and I can generate all the same vectors that I want in the same space, right? And I don't need the other two. Okay. In fact, if I cut out, we already know the second one is a multiple of the first, right? So we can throw out that one for sure. If I leave the last vector in there, right, and I row reduce, right, so it's augmented here, then if I multiply the first one by -6 and the second one by 2, I get the last one. So if I multiply, so this tells me -6 times the first vector plus 2 times the third vector is going to equal that last vector. Is that true? Yeah. So that last vector we can write as a linear combination of the first and third vectors. That means we don't need that last one. Right. We just need the first and third one, and we can generate all the same vectors. When we span them, we get the same set as if we'd spanned all four of them. Okay. So if you have a set of vectors and you span them, you get a subspace. A basis for that subspace would just be the linearly independent vectors out of that set. Okay. If they're all linearly independent, then you have to use all of them. But we only found 2 out of this set, so we don't need the rest. Any of the dependent vectors we can write as a linear combination of the independent ones. That's all we need. The answer is this right here. So that's not enough to span R3, but it's all we need to span the subspace that you get when you span those 4 vectors. If I span the 4 vectors, I get a subspace. I just need those 2. I didn't need all 4 of them. Okay, 4 was too many. Okay, I'm going to stop.